Good morning. So, we will continue about the clutch design aspect. So, these are the topics we have been covered so far. So, particularly we are discussing about the torque transmitting capacity aspect for various clutch type, for single plate clutch, multi disc clutches, cone clutches, and today we are going to learn about a centrifugal clutches aspect. Before going to understand about the centrifugal clutch, I would like to play a video for you. You can see this is the video.
In this video, we are going to learn how a centrifugal type clutch works. The main function of a clutch is to engage and disengage the mechanical link between two rotating machine parts. A clutch can be operated manually or it can be an automatic type. In a typical motorbike clutch unit, clutch is kept engaged with the spring pressure. Thus, power is sent to gearbox from engine. Generally, a centrifugal clutch is designed to work automatically, depending on centrifugal force. When an object starts moving in a circular or curved path, a type of force keeps pushing the object outside of that path. This is called centrifugal force. Centrifugal force depends on the velocity of the moving object, radius of curved path, and the mass. That means, for a rotating object, if rotational speed increases, then centrifugal force increases too. Centrifugal force can be fun, or, ignoring or not knowing this basic physics stuff, can be very dangerous for you in some situations. Or centrifugal force can be used with brilliant engineering technique, just like in centrifugal clutch. A centrifugal clutch consists of different parts. Its inner hub is powered by the engine output shaft, and the outer drum is connected with the transmission shaft. In this type of design, a number of mechanical shoes are installed on the inner hub plate. These shoes can rotate from the hinged points, but tension springs keep it away from the drum's inner surface. The inner hub assembly with the shoes starts rotating along with the engine shaft. When rotational speed increases, centrifugal force makes these shoes turn against spring force. These shoes' lining creates frictional grip with the drum's inner surface, so it makes the outer drum rotate along with it. Thus, power is transmitted through the centrifugal clutch. Centrifugal force reduces when the engine shaft speed drops below a certain limit. Spring force pulls back shoes from the drum surface, and the drum becomes free. So the transmission shaft doesn't get affected by engine braking load. Similarly, during starting the engine stays free from driven load, so the engine can be started in no load condition. When engine RPM reaches a certain limit, the centrifugal clutch automatically engages and starts transmitting power to the driven unit. Thank you for watching.
So, that is about the centrifugal clutch. So, in fact, I would like to show, I think I have shown this also earlier. You can see in the video, you have seen it, right? In the video, this is something shoe, it is called shoe. You could see, right, this is one shoe and 2 and 3, all 3 shoe get together in constraint with the spring. This is the spring. So, again the number of shoe will vary, depends on the how much torque you want to transfer, right. It can be 3, it can be 2, it can be 4. Probably you could see this is actually 2 shoes constraint centrifugal clutch. In fact, I think I have shown you this also earlier, right. This is nothing but your centrifugal clutch. So, this is your drum, right, and this is the one which is going to fixed with your engine. Sorry, this is to the drive shaft where you wanted to driven shaft where you wanted to transmit the power to the gearbox, right, and this is the one which is going to be fixed in the engine side. And you can see that there is a 2 lobes, clearly the 2 lobes are there, and 2 lobes are connected with your spring. In fact, each lobe will have a friction lining, right. As rotation, right, due to centrifugal force, this is tried to expand against the spring force. So when the centrifugal force same as a spring force, then it will start floating. If the spring force greater than the your centrifugal force, it will be intact, right? As increasing the speed, the centrifugal force keep increasing. At one stage it will be equal. After that it will be greater than the your spring force. At that condition, it try to expand, right? And expand radially. It expand radially such way that make a contact through friction landing, right? Then transmit the power. Okay. So what is the advantage? You can operate the system without loading condition and make the transmission very smooth. That's the purpose, having a centrifugal clutch aspect. And you can see here also, this is a typical schematic diagram where you have a shoes, right? This is your drum, and the entire arrangement is called as a spider. Shoe with the spring is called as a spider, and they will always have a spring, right? Because that is the one which is controlling your centrifugal force aspect. Okay. So before going to the centrifugal force, yesterday lecture I have discussed about the cone clutch aspect, right? I discussed about the cone clutch aspect. So I said cone clutch is extensively used. One of the application is a synchro mesh gear. This is nothing but your synchro mesh gear. This is actually the gear, right? You can see this is the gear, and the gear will have it's helical gear. You can see that this is attached with this cone. If you look at in this direction, you can see that there is a small angle. Tappet, you can see the tappet. This is nothing but the cone arrangement, and top of that, this is the blocker ring. If you look at internally, this also is a cone type. So they will make nice contact so that there won't be any slip and make the transmission. In fact, maybe I will show. This is the synchromeasure aspect, and this is the hub, and they will make a contact through blocker ring and transmit such a way that the speed of the gear and the speed of the shaft will be same. That's why it's called synchronizer. Okay. So in the synchronizer mechanism, extensively used a cone type of clutch arrangement. Okay. So when now I think I have discussed in the class, whenever you say constant mesh, the constant mesh can be a dog clutch arrangement. The another one is the synchro mesh arrangement. Okay, the synchro mesh is very smooth, less noise, very compact for human, for a comfort level aspect. Okay, so this is again an example for the synchro mesh with the cone clutch arrangement. Okay, now we understand the centrifugal force which is causing to move the entire spide through shoes, right? So that means we need to understand how much the mass we need to know. So suppose we want to transfer fixed amount of torque, right, for the engagement. So we should aware of the how much torque we need. So what would be the mass of the shoe? How many shoes you need? Then what would be the dimension? So those aspects we are going to learn from today's lectures. So I will draw the schematic diagram, right. So just before giving, I will introduce the dimensions. So take the RD. RD is the radius of drum. Radius of drum. RG is the radius of center of gravity, okay, of the shoe engagement. CG, center of gravity, okay, of the shoe in engagement, during the engagement. M is the mass of shoe. I am talking about only single shoe, okay, not the entire one. And PCF, centrifugal force, right. PS is a spring force, and W1 omega 1, okay, speed at which the engagement start. And omega 2 is the running speed. Yeah, right. You can see this is the just nomenclature. RD, RG, M, PCF, M, PS, omega 1, omega 2. So now I will draw this schematic diagram and the forces also. So assuming this is your drum, right? This is your drum. This is your drum arrangement. Yeah. Like this, okay. So there is a shoe at the center. So it has some mass, and this is your CG, right? This is your CG, and this is connected through spring, right? This is what happening, okay. So this is connected to spring. This is drum, okay, and this is a certain angle. So the shoe angle, you can say theta. At the moment you are not considering, and the dimension between center to here, this is your drum diameter RD, right. The CG will flexible, so it's change, depends on the things, okay. So this is your RG, radius of due to gravity aspect, okay. And if you look at the, just I wanted to show the force balance. This is your the mass, shoe mass, okay. This is your CG, okay, right. So usually what happens, the spring try to pull inward, right. So you will have your spring force PS, right. But as you increase the speed, it will move upward direction. So this is your centrifugal force PCF, okay. So when do you expect engagement, right? When you overcome the PS, right, that means there is a net force during the engagement will then will make a contact through friction. So that should be your PCF minus PS, right, PCF minus PS, right. Then I am not saying PCF the later stage, okay, and that is your mu, that is your mu, okay. So when you talk about, so initially you will have one centrifugal force at the beginning of the speed, at the end of the speed you will have another centrifugal force. So we will say that PC2 aspect, PC1 is the initial one, yeah. So the centrifugal force at the beginning, okay, omega 1 at speed. So what do you expect, a PCF 1 m into omega 1 square r g, right. Again depends on the your radius, which is the center of gravity, okay. Similarly centrifugal force at the running speed where the engagement happened, right. This is before the engagement, and this is a thing which is omega to speed. So obviously PCF 2 m omega 2 square RG. This RG also will variable, okay, it's a variable. So the centrifugal force is balanced by an equal and opposite spring force. Initially PCF1, right, is balanced by an equal and opposite spring force PS, right, at the beginning of the engagement. So your PCF 1 equal to PS equal to m omega 1 square Rg, right. Okay, so the moment, right, as speed increasing, right, the PCF will start 1 will greater than your Fink's force. That's what happening. So okay, so that's where, so when in this condition the shoes moves radially outward and make a contact with the drum through friction lining, right, through friction lining. That's what happening, okay, through friction lining. Okay, so then the net force during the engagement, the net force Pn should be your PCF 2 minus PS. Yeah, this is m omega 2 square, then this should be Rg, this should be, right. So what do you happen to, yeah, where is the PC? What is the PC? PC is nothing but your PCF 1, right. After that only it will make engagement, before that won't. So this should be equivalent to PCF 1. So when you rewrite m omega 2 square Rg minus m omega 1 square Rg, and you take it out commonly m Rg, then it should be omega 2 square minus omega 1 square. So this is your net force, right, the net force acting on the drum. That's a equation number 1, we can say that. But this is just a force, but this is happening through a frictional aspect, right. So therefore the frictional force will be mu times your Pn, right, mu m r g. Okay, this is fine, frictional force is fine. Now I need to find as a frictional torque now. T, right. So what is the frictional torque? Mu Pn, right, into the frictional torque with respect to your drum diameter, right, Rd. So if you rewrite mu m Rg Rd 1 square, this is what happened. Okay, so this is the entire thing. Okay, this is for the one shoe, right, for Z number of shoes, right, number of shoes, then the total torque capacity, frictional torque capacity of the centrifugal clutch right is T equal to, right, mu m r g r d z omega 2 square omega 1 square. So this is the equation, we should use it. So this much torque is transmitted through shoe clutch arrangement. Okay, the question is, so what is the application? Any idea what are the application? You want to have a smooth engagement, right? Where do you expect? Have you seen how the cranes operating? The cranes and hoists and all, how do they operate? They have to supply, get the power from the motor, right? How does it happen? That is through this centrifugal clutch. You don't want to, you want to have the transmission very smooth with the low load condition. In that condition, mostly the preferred clutches would be the centrifugal clutch. Okay, so you can have a cranes, ball mills, all cement mills for heavy duty application, and also you can have a lawn moves, lawn mower where you want to cut the grass, right? There also they used the centrifugal clutch. How about go-kart? Have you been to go-kart? Right, they are connected with the electrical thing and you keep that's one way, or else there is a small pit that's also do that, which they use pretty much the centrifugal clutch. Okay, yeah. So that is about the centrifugal clutch. We will do a couple of problems. Then tomorrow we'll start the dynamic and thermal analysis of a clutch system, which is very important. Yeah. So can you take down the problem, please? Question number 4. A centrifugal clutch transmitting 200 kilowatt at 750 rpm consists of 4 shoes. The clutch is to be engaged at 500 rpm. The inner radius of the drum is 165 millimeter. The radius of center of gravity of the shoes is 140 millimeter when the clutch is engaged. The coefficient of friction is 0.3, while the permissible pressure on friction lining is 0.1 Newton per millimeter square. The shoe angle is given 70 degree. Calculate the mass of each shoe and also find the dimension of the friction lining. So we have to find out the dimension for the friction lining also, right. So there is a transmitting power is given. So transmit power is given 20 kilowatt, operating 750 rpm. The number of shoes are given 4. The initial speed is given 500 rpm and the engagement speed 750 rpm. The inner radius 165 mm. Inner radius of the drum RD is given. The RG is given 140 mm, that also given. Mu is 0.3. Then permissible pressure PA 0.1 Newton per millimeter square, and theta, the subdued angle of the shoe, is 70 degree. Okay, we need to find out, solve the problem. It's a very simple problem. It's very straightforward. First, we have to find out the mass, right? So we need to know that the first condition, T equal to m into, I would say mu m rg rd z omega 2 square omega 1 square. I think this is the formula, right? This is the formula. T is we will find out what is the T. You know mu is given, rd you know, rg also known, z is known, omega 2 known, omega 1 also known. So you need to find out the mass. Okay. The power, right? The power is 20 kilowatt. N2 750 rpm, N1 500 rpm. Z is number of shoes, is given 4, right. Then radius of drum 165 millimeter, radius of the center of mass Rg 140 millimeter. Yeah, mu is given 0.3, the allowable permissible pressure 0.1 Newton per millimeter square. Okay, just we will find out the omega 2, 2 pi n2 by 60, 750 by 60, and omega 1 similarly 2 pi n1 is 500 rpm, right? 500 by 60. So I would, you think you should get 78.54 radian per second, and this should be 52.36 radian per second. It's clearly given. Okay. So when do you expect the power transmission? When do you expect the power transmit? Right? Yes. Yeah, okay. No, which speed? That's a question. Torque into the final speed, omega 2, right? That's the speed, the power is transmitted, not before that. So, the 60 already given, so 20. So, we need to find out the torque, okay. So, T equal to your power by omega 2, that is 20 kilowatt, right. So, omega 2 already we know 78.54, that should give 254.65 Newton meter. This much torque is transmitted. Yeah. Now we know T equal to mu m r g r d z omega 2 square omega 1 square. Substitute and tell me what is the m value. Right. So 254.65, mu equal to 0.3, right? Yeah, 0.3. M we don't know. RD is given 0.165. Yeah. And your RG is 0.14. And number of shoes are 4. Okay. And this should be 78.54 whole square and minus 52.36 whole square. Okay. So, can you have what is the value you are getting for the shoe mass? 2.68 kilo, 2.68 kilogram mass. That is the mass of the shoe. Okay, that is fine. So, the next step would be we need to find out the dimension of the brake lining, right? Dimension of the brake lining. Friction lining. Here is clutch purpose, so we don't want to say brake lining, better it will say friction lining. Okay. So, actually this is just give you a schematic diagram. Okay. This is the arrangement, right. So, this is your theta 70, that is clearly given, and yeah. Yeah. Right. So, this is your drum RD. Okay. I am just showing in 3-dimensional. This is the arrangement. So, this is your friction lining, right. This is your friction lining. I am just showing the things. So, this would be your face width and this would be a arc length, right. That will be L, arc length, L you can say that. Yeah. So, what happened? L equal to the theta, right. So, this is 16 theta 70, right. So, we can't use 70 just like that, it has to be in radians. Okay. 70 by 180 into pi. So, that will give you information. So, what is the value you are getting? L equal to what? L equal to, we should get 0.2 meter. So, that is the value you are getting. The length of the arc length of the friction lining. So, that we know that, so but we do not know about the face width, right, but you got the pressure, the friction lining pressure is given, right. So, the net force acting on the friction lining, right, on the drum and the lining also together should be equivalent to your allowable pressure, right, allowable pressure. So, that is right into friction lining area. So PA into L V into B. This is your arc length L and this is your projected length, projected area B. So that is clearly given. Right. This is your net acting force. So PA is given, right? PA, you know that PA is given 0.1 Newton per millimeter square. That is clearly given. Okay, tell me what is that value you are getting? How do you find that net acting force P? Find out the net acting force. From there you do that. It's much easier. So net acting force, maybe I can rewrite. Okay, equal to m Rg omega 2 square minus omega 1 square. That should be equal to Pa into L into B. Substitute please, and substitute, and you know omega 2 is known to you, omega 1, m Rg all are known to you, Pa also, El, just find out the B please. This should be 2.6, right? The mass value, that is what we find out. So 2.68 into Rg 114, and this is should be a 78.54 square, 52.36 square. This is 0.1 into 10 power 6 please, because everything we are doing into Newton meter, and this should be 0.2 and this should be just B. So what is the friction lining width you are getting? 65 mm? Yeah, in mm 65, right? Yeah, okay. So you get 0.06 meter, or else the friction lining 65 mm. So now we know L also 200 mm. So these two are friction lining dimension. Okay, friction lining dimension for each issue, right? For each issue, the same thing we need to do the for other things also. Okay, I think another small problem. Just I'll just discuss with you, and then maybe you can do it later stage. A centrifugal clutch consists of 4 shoes, each having a mass of 1.5 kg. In engaged position, the radius of the center of the gravity of each shoe is given 110 millimeter, while inner radius of the drum is given 140 millimeter. The coefficient of friction is 0.3. The preload in the spring adjusted in such way that the spring force at the beginning of the engagement is 700 Newton. The running speed is 1440 rpm. Calculate the speed at which the engagement begins, which is omega 1, and also what would be the power transmitted by the clutch at 1440 rpm, which is they are asking about the P power, which is torque into omega 2. This is a very simple problem that you can do it as a homework. Okay, and tomorrow I will stop now.